In this video, we continue our study of Chapter 13 on the properties of mixtures. We're going to go through colligative properties and colloids, but before we do that, we're going to review a little bit from our last video, and we're going to introduce a new term. So here are enthalpy diagrams for our three ionic compounds dissolving in water. As we saw before, we have sodium chloride being slightly endothermic, near thermoneutral, sodium hydroxide being highly exothermic in dissolution, and then ammonium nitrate being highly endothermic. So when you dissolve ammonium nitrate in water, you feel the solution cool down substantially. As a general rule, enthalpy tends to decrease in a lot of chemical reactions. And so there must be some other driver involved here, and this introduces a new concept that we're going to cover this chapter, particularly in much more detail in a few weeks, and that is the concept of entropy. Entropy turns out to be very important for solutions. Entropy is given the letter S, and it's a thermodynamic function. It's a state function, just like enthalpy, H, we learned about back in Chapter 6. And just like enthalpy can be thought of as, enthalpy change is thought of as heat at constant pressure, entropy has a simple way to visualize this, and it is related to the number of ways a system can exist or disperse its energy at a given total energy state. And so it's related to the kind of degrees of freedom or the freedom of motion of the particles. Thus, if you have a gas, so if you have a container of gas, at a given temperature, there needs to be a distribution of speeds of gas molecules in that container. But of course, there can be a very large number of ways to distribute the molecules' speeds and positions inside the container for a given energy or a given temperature and a given pressure and volume. So it turns out gases have a very high entropy. They have a large value for S. So a very large positive S is a favorable thing, and that's what happens in this case. Now for liquids, they tend to have much lower entropies, but we find out that solutions, that is mixtures of a solute and a solvent, generally have a higher entropy than the sum of the pure solute and the pure solvent themselves, because again, we can, under a given set of temperature and concentration conditions, the solution can exist in a variety of different positions and distributions of particles, whereas the pure solute and pure solvent cannot. So generally, an increase in entropy is favored in both physical and chemical processes. So systems change toward a state of lower enthalpy and lower enthalpy and higher entropy. So the sizes of delta H solution and delta S solution determine whether a solution forms. So popping back up to our ammonium nitrate case, even though this reaction, dissolution process, is very endothermic, the delta H of solution is very positive. It turns out that the entropy term is also very large and favorable to counterbalance this. And so we'll see that the delta S is large for that and positive as well. So we'll see how that works out in a few weeks. We're going to look at one more enthalpy diagram, and that is for dissolving sodium chloride in hexane versus dissolving octane in hexane. On the right-hand side, we have sodium chloride going into hexane, and you can see at the bottom we have hexane in the aggregated in the liquid state, and sodium chloride aggregated in the solid state. There's an enthalpy term to separate the hexane, which is relatively small due to the London forces, and then the lattice energy for breaking up sodium and chloride. So the total of those two terms is our top black line. If we add that together and then bring in our delta H of mixing, which is relatively small, because now the sodium is interacting with hexane, which is only an ion-induced dipole force, and that's one of our weaker forces, the delta H of mixing is relatively small, negative. So overall, the delta H for our solution in this case is very large positive, and that cannot overcome, that the entropy term does not overcome that. And so we find that salt does not dissolve in hexane or in gasoline in general, in nonpolar solvents. Now on the right-hand side, we have hexane and octane. Both of those aggregation, breaking those up, the delta H solvent and delta H solute are relatively small. And then when we recombine them, the delta H is actually slightly negative. And of course, we have a good entropy term, and so octane does dissolve readily in hexane. So like dissolves like. So thinking about the solubility in a little bit more detail, imagine you take sodium chloride and you throw it into water. Now, let's say that you like really salty water to cook in, so you throw a whole canister worth of Morton salt in, so that you have some salt sitting at the bottom. You would have created a saturated solution. That would be water that contained the maximum amount of dissolved solute at the temperature that you're at. And then you're also in the presence of some undissolved solute. That is a saturated solution. Now, a saturated solution is not a static system. It's a dynamic system. It turns out this is what we call a dynamic equilibrium. Some of the solute that is dissolved in solution will fall back out or precipitate from solution, but at the same time you'll have some salt ions that will be going from the solid state into the dissolved state. And we have ways of keeping track of this. You find that atoms will move from the dissolved state into the solid state and back again in this dynamic equilibrium. That's a saturated solution. An unsaturated solution has less than the equilibrium concentration. And it turns out in this case, nothing precipitates out. The ions stay in solution in a constant state. And if you add more solute, you can increase the concentration. It'll dissolve. Now, you can have a supersaturated solution, and your textbook talks a little bit more about that. If you heat a solution up, generally, you see that if you have a solid as a solute, its solubility will increase. And that's shown on the graphic to the right. You can see that the solubility usually increases as a function of temperature. So for example, sodium nitrate, the top line, you can see that the solubility concentration goes up significantly as the temperature increases. It's not always the case. Sulfates very often have negative coefficients of solubility. Their solubilities tend to a lot of times decrease as the temperature goes up. But for most solids, the concentration, the solubility limit goes up as the temperature goes up. Gases, on the other hand, tend to become less soluble as the temperature goes up. So the next time you have a Mountain Dew, take it and gently pour it into a pot and put it on the stove and take it up to near the boiling point, and then cool it back down, put it in the refrigerator, and you'll have a nice cool Mountain Dew. But all the carbon dioxide that was dissolved at low temperature will come out of solution at high temperature, and when you cool it back down again, you'll have flat Mountain Dew. The next factor we're going to look at is the effect of pressure on gas solubility. We saw in the last video that nitrogen is soluble in water. And it's not highly soluble, but it does dissolve. But if we increase the pressure of the nitrogen above the water, you can push more nitrogen molecules into the water. So we find that as the pressure increases, the gas particles will collide more with the surface, and the gas will dissolve more into the solution, so the solution concentration will increase. And that's described by something called Henry's law. So Henry's law states that the solubility of a gas, that is S sub gas, is directly proportional to the partial pressure of the gas, P gas, above the solution. So here's an equation that you need to know and you will use. The solubility of the gas is equal to a constant of proportionality, that is K sub H, the Henry's law constant, times the pressure of the gas above the solution. Graphically, we see here, as the pressure goes up, the solubility goes up for oxygen, nitrogen, and helium. And larger KH, which is the slope of these graphs, indicates a greater gas solubility. We're going to segue into colligative properties, but before we do that, we need to refresh our memory about concentration units and bring in a couple of more concentration units that are important. Back in the end of Chapter 3 and Chapter 4 in Gen Chem 1, you learned about molarity, which was an expression of concentration for a solution. The unit is defined as the amount or moles of solute per liter of solution. So it's a very easy to use unit. We use it all the time in lab and use it for industrial processes very often. Easy to use, but it's very temperature dependent, because as the temperature goes up, the volume of a solution will increase, but the moles won't go up, so the concentration drops. So we have another unit called molality, and molality is a temperature independent unit. It's more difficult to use, but it does have this temperature independence, and for precise measurements, it's very often useful. So this is given as the amount or moles of solute per kilogram or mass of solvent. And since moles and kilograms are temperature independent, you can see molality as temperature independent. Next, we have the parts by mass. And this would be like the mass percent we learned back in Gen Chem 1, the mass of solute divided by mass of solution. Now, to have a mass percent, you need to multiply that value times 100. You can convert that to parts per thousand by multiplying it by 10 to the third. You can convert it to parts per million by multiplying it by 10 to the sixth. Or you can convert it to parts per billion by multiplying by 10 to the ninth. You can also do this for gaseous or liquids that you mix in other solutions. And we use parts per by volume as a unit. That is the volume of solute per volume of solution. This can also be done for gases within gases. Finally, we have mole fraction, which is a term we have been introduced before, but we'll use it quite a bit more this semester. That's the moles of solute divided by moles of solute plus moles of solvent. So that's a fractional value between 0 and 1. Now, we're not going to do this in this video, but we'll spend some time in lecture, and you'll have a chance to practice this with homework problems, interconverting between these concentration units using molar masses and densities. We use these units very often to study something called colligative properties. Colligative properties are properties of a solution that depend only on the number of solute particles that are present, not on the chemical identity of the solute particles. So the colligative properties will only depend on the solvent and the number of particles dissolved in that solvent. And so you'll find out, for example, if you dissolve methanol, then methanol, each molecule of methanol that goes in gives you one particle. So you get 1 mole of particles per mole of methanol. If you dissolve sodium chloride, you'll get 2 moles of particles, 1 mole of sodium ions, 1 mole of chloride ions. If we use magnesium chloride, we'll get 3 particles, 1 mole of the magnesium 2+ ions, and 2 moles of the chloride, Cl- ions. As we study this, we're going to look primarily at strong electrolytes and non-electrolytes. Strong electrolytes are ones that dissociate completely into ions, and these include soluble ionic compounds, strong acids, and strong bases. Weak electrolytes are generally the weak acids and the weak bases. And we'll defer study on those to a later chapter this semester. And then non-electrolytes like methanol don't dissolve at all, or don't dissociate at all. They do dissolve, but they just the number of particles is equal to the number of moles dissolved. The first colligative property we're going to look at is what's called vapor pressure lowering. The vapor pressure of a solution containing a non-volatile electrolyte is always lower than the vapor pressure of the pure solvent. We learned about vapor pressure back in chapter 12, and the Clausius-Clapeyron equation gave us a chance to see how that relates. When the vapor pressure of a liquid equals the surrounding atmospheric pressure, the liquid would boil. So when water reaches a temperature of 100 degrees Celsius, its vapor pressure equals 1 atmosphere, and it will boil. If we, however, add an electrolyte, water will not boil. It has to go to a higher temperature than 100 degrees Celsius to boil at 1 atmosphere. The vapor pressure is lowered anytime we add a non-volatile non-electrolyte. So Raoult's law states that the vapor pressure of a solvent above a solution is proportional to the mole fraction of the solvent present. So here is an important equation that you should know. P solvent is the vapor pressure of the solvent under the given conditions, and that's equal to the mole fraction of the solvent, which is a value between 0 and 1, generally relatively close to 1, multiplied by the vapor pressure of the pure solvent, that's P0 solvent. We can rearrange this and come up with what we call the vapor pressure lowering. The amount that the vapor pressure is lowered is proportional to the mole fraction of the solute present, and that's given by the following equation. Delta P solvent, that is the lowering of the vapor pressure of the solvent, is equal to the mole fraction of the solute times P0 for the solvent. And this picture illustrates this. Above pure solvent, you have a certain number of particles present, but if you throw in a non-volatile solute, then of course the vapor pressure goes down. There are fewer particles present, and there's fewer particles above the solvent as well. The next colligative property we're going to look at is boiling point elevation, which is related to what we just looked at, because boiling point is the point at which the vapor pressure of the solute under the given solvent under the given conditions is equal to the atmospheric pressure. A solution, since the vapor pressure is lowered, always has a higher boiling temperature than the pure solvent. This colligative property is a result of the vapor pressure lowering. So here's an important equation. The boiling point elevation, that is delta T sub B, which is a positive value, is proportional to the molality of the solution times a constant of proportionality K sub B. K sub B is called the molal boiling point elevation constant for the solvent. Now, correspondingly, when you add a solute, the freezing point goes down. So a solution always freezes at a lower temperature than the pure solvent, and it is for the same reasons we saw just a moment ago. Freezing point depression also is proportional to the solution molality, and it's given by this important equation that you should know. Delta T sub F, which is going to be negative, is going to be equal to K sub F times the molality of the solution. Kf is the molal freezing point depression constant for the solvent. Now, if you use K sub F as a positive value, delta F will be positive, but that is the amount that you decrease the freezing point for your solution. And we can understand this if we go back and look at a phase diagram for a common liquid. So here's water. We see that we're looking at the phases of the system as a function of pressure and temperature. We have our yellow gaseous region at low pressure and higher temperature, the solid at lower temperature and higher pressure, and the liquid at the intermediate and higher regions of temperature and pressure. The solid lines are for pure water. And where all three lines meet, that's the triple point. Now, if I add salt to the water, what happens? Well, it lowers the vapor pressure, and it increases the boiling point. And since the vapor pressure has lowered, you see the dotted line. So the lower dotted line with the delta P shows how the vapor pressure has been lowered. And in fact, that carries through to the solid as well. It's effectively reduced something we call the chemical potential, which you would learn about in physical chemistry. And so you see that the liquid is more stable over a wider range when you add salt. So this is why you throw salt on ice or snow to melt it. And that works for a while unless the temperature gets too low. And that lowers the freezing point, so your ice can turn to liquid and you can have better driving conditions. And then when you add salt to water, it also increases the boiling point slightly. So that's a way to increase the temperature that you're cooking at. So here are some constants for your freezing point depression and boiling point elevation. You don't need to know these. You would be given these, but you should look through them to get some sense of what these numbers look like. These are the boiling points, and then your molal boiling point constants and freezing point constants. We'll do practice problems on these in class. Our next colligative property is osmotic pressure. Osmosis is when liquids, particularly a solvent molecule in one region, moves through a membrane to a region of higher concentration. And typically there'll be a semi-permeable membrane which will allow the solvent to move, but not allow solute to move. And you will see that the solvent will move from the pure region to the region that is impure, where the solute is present. So the solvent always flows from the more dilute solution to the more concentrated one. Osmotic pressure, then, is the pressure that you have to apply to prevent the solvent from moving from the more dilute to the more concentrated region. And that's given by the following equation. Pi is the osmotic pressure. It's equal to m, which is the molarity of the solution, times the gas constant, times the absolute temperature. Looks kind of like the ideal gas equation without a volume term. But of course you have molarity, which is moles per volume, so it is somewhat of a rearrangement. But this is not for gases, this is for liquids. And here's how this looks. So on the left hand, you have a U-tube, and you've thrown in a solution and pure solvent. You start off with equal heights, but if you let them sit there, liquid will move from the pure solvent region through the black semi-permeable membrane into the solution side. And you'll notice that the liquid level on the solution side will rise up. In the end, it'll rise up to a height that's equivalent to the osmotic pressure, and then it will stabilize. If you want to drive liquid back through, you have to apply pressure on the solution side, and then you can drive pure liquid back into the left-hand side. This is actually the way for doing water purification by using osmosis. But applying a high pressure, of course, requires energy. Now, if we have a volatile non-electrolyte solution, then what happens is the electrolyte that's in the non-electrolyte, that is the solute, can vaporize just like the solvent can. So the vapor above the solution will contain both the solute and the solvent. This is like, for example, dissolving octane into hexane. Both octane and hexane are volatile. The presence of each volatile component will reduce the vapor pressure of the other, since each one lowers the mole fraction of the other. So you actually end up with something that is lower than what you might predict simply on the basis of the vapor pressures of each of the individuals. For such a solution, the vapor will have a higher mole fraction of the more volatile component. So for our hexane-octane case, hexane has a lower boiling point, that's more volatile. So the gas phase, the vapor phase, will have the higher mole fraction of hexane than does the solution of octane and hexane. So the bottom line is the vapor has a different composition than the solution does. Now, strong electrolytes, of course, the electrolyte is non-volatile. So strong electrolytes completely dissociate to form ions, and each mole of solute gives them more than one mole of dissolved particles. And you'd think from the formula we can simply predict what we have. Each mole of sodium chloride gives us 2 moles of dissolved particles. But your colligative properties don't follow fully 2 moles. It turns out that you get a little bit less of effect than 2. And there's something called the Van Hoff factor, that is I, which is the ratio of the measured value for the solution divided by the expected value, which is generally going to be a value less than 1. This takes account of the dissociation of the strong electrolyte, and this is really measuring something called the activity of the solution. So the vapor pressure lowering, we think of that as being chi solute times P0 solvent, needs to be multiplied by little I, which is a fractional value, to show us the decrease relative to what we predict. So for example, with magnesium chloride, we might think of 3 particles. Well, we actually end up with slightly less than a factor of 3 factor in affecting. And then for boiling point elevation and freezing point depression, we have similar equations, and finally for osmotic pressure as well. So you should know all these relationships. You simply put I in terms of the 4 relationships we mentioned earlier that you need to know. So you can use these. And here you see this, sometimes, there's something called the ionic atmosphere effect. Ions will tend to get close to one another, even though they're not fully bonded or bound together. They will attract one another in solution. And so that ionic atmosphere decreases the effect of the number of particles. It's also something known as an activity effect. So here you can see that iron 3 chloride has an I value of 3.4. Magnesium sulfate has a factor of 1.3. Magnesium chloride is at 2.7 instead of 3. Sodium chloride is 1.9 instead of 2. Hydrogen chloride or hydrochloric acid is 1.9 instead of 2. Now, glucose and non-electrolytes, their I value is always equal to 1. So for colloids, this is our last topic. We're going to think about these. These are special types of materials. If you drink cow milk, that's a colloid. It's a heterogeneous mixture. It's not a homogeneous mixture. It's not a true solution, because you have a solvent, but then you have particles that are really effectively solids or very viscous gels that are dispersed in the solvent. They're not fully dissolved. And if you've seen a cloudy solution before that stays cloudy, that is generally a colloidal solution. You've got particles inside water that don't settle out. Particles are typically macromolecules, aggregates of small molecules, or very, very small, what we call nanocrystallites, that are dispersed. And typically they're so small, they're typically under 100 nanometers, or on the order of a couple of 100 nanometers. So they're so small that the solvent molecules can bump into them and keep them in solution. They're undergoing something called Brownian motion. And here's a series of different colloids: aerosols, foams, emulsions, and gels. The one I put in black is the one that's probably the most important one. That's a solid dispersed in a liquid, like paints, cell fluids, blood. And so that's what these look like. Now, you may have heard the phrase nanotechnology or heard of nanomaterials. Nanomaterials, in some sense, are colloids that happen to have very narrow size distributions and are very well behaved, and typically have sizes between 1 and 100 nanometers. And here are examples of colloidal dispersions. On the left-hand side, you have a light beam passing through two solutions. The solution on the left is a homogeneous solution, and the one on the right is a colloidal dispersion, so it looks cloudy. The light particles bounce off of the particles in solution and give the appearance as such. And then the picture on the right-hand panel shows a forest, and there are dust particles and likely other aerosol particles, maybe limonene, pinene, sort of organic particles coming off of the tree leaves or pine needles or conifer needles, as well as water droplets and dust particles. And they're all particles in air. Those are colloidal dispersions. So they're not truly solutions. They're colloids, and they have their own set of properties. That's the end of chapter 13.